The TCP/IP network and data link layers dominate the points available to you on your CCNA exam. Start learning about those two layers right now. Let me start by setting a little context for the course. We're in the first video of the course, and I organized this course to match the organization of the official Cisco Press CCNA Cert guides. So this content mirrors the content that you'll find in Volume 1, Part 1, Chapter 1, indeed even in the first section. So what do you find in that chapter? Well, you find two sections, the first of which is titled TCP/IP Networking Model. So what I've done is looked at the content there and made a video that presents the information a little differently than the book. In fact, I start out with an analogy that you don't even find in the book, comparing networking to a shipping company and how they do things. Then we get into the detail that has to be the same because you need the facts about how the TCP/IP networking model works. But I focus on the network and data link layer models, comparing that to how we ship packages. In each video, stick around to the end for a few extras. For instance, in the opening, I told you that most of the points for CCNA come from two layers of the TCP/IP model. What percentage? Well, I plugged it into a spreadsheet. I'll talk about that at the close. But for every one of these, I'll end with a couple of comments, one about the books. If you have the books and you're using them, I'll give you some advice about having watched a video about some of the same content. What else in the book should you look for to make sure that you read? Also, for everybody, I'll close with some pointers to a review exercise so you can study and remember what you heard in this video. All right, let's get into the good stuff. Let me start this video about computer networking by talking about something other than computer networking. Let's talk about an analogy to computer networking, which is shipping, how we ship boxes and packages to each other, or maybe an e-commerce site ships something to you that you order online. So here's some big ideas with that. They promise to send a box, the shipping company, from wherever it's sent to wherever it needs to be received, right? And they own some trucks and planes and boats and things like that. And they employ people that will drive those trucks and planes and boats around. And they employ people that work at these big buildings with sorting machines that will look at the boxes and move them around. And you as a consumer of their service, you don't need to know. In fact, you could have no skills at driving or flying a plane or floating a boat, right? You just know that it works. But you know that, for instance, you need to, get a box. And you need to follow the rules about the shape of the box. You need to put a shipping label on it. And you need to pay them some money so they'll, be willing to send the box, that kind of thing. From the shipping company's perspective, though, it's a series of activities that's move the box to a building, sort it, move it to another building, sort it, and on like that. Using this diagram then to show the big ideas, the shipping company works on a model, for instance, where the person sending the package asks the shipper to come pick up the package and deliver it to some faraway postal address, right? That's the big idea. But the shipping company thinks of it as a series of movements, right? Move it to their first distribution center, then to the next distribution center, and the next one. So they think of that as forwarding or routing, if you will. But then the boxes can't move by themselves, right? They're just inanimate objects. So we've got to put the boxes inside something that can move. So there'll be a series of vehicles like small trucks and big trucks and airplanes and the like that actually move the box through their system. Another perspective in this analogy is that you care more about the contents than the shipping company does. For instance, Cisco sent me this nice mug years ago, the folks in the CCIE program. They're really great about staying in touch with CCIEs after you get your certification. It's really kind of them. But they couldn't take this mug, which is glass, and just put it outside the curb from the Cisco office and let the shipping company then try to deliver that, right? We're going to need some packaging, maybe this, really inexpensive paper that we jam down in here. But we might even want some bubble wrap, something much more secure. We put that all inside the box. You get the idea, right? We've all done this a million times at this point in our lives, right? But we care about that. And then as long as you follow the rules about wrapping it up, then the shipping company says, here's a box. It was delivered. It had the appropriate label. Let me ship it through the network. Now, as long as you paid the bill, they'll deliver that. But it's the endpoints, say the person you bought something from online, or you as the receiver of that product, you care more about what's inside. So there's a different perspective on the shipping system for the sender and receiver that you care more about the insides, whereas the shipper cares about getting the box from the sender to receiver. To show that visually, imagine that box on the far left. We want to get it into the shipping system. Well, you get the box, you take the thing like my glass mug, you put some packing material around it, you put a valid shipping label on it, and that's what you hand off to the driver of the truck that comes by your apartment or house each day to get it into the system. All right, so those things are pretty obvious, but those things do link into how modern networking works. So just to complete the analogy a little bit before we dive into TCP/IP, there are different workers that make this happen in the shipping system, right? So if you think of that model that we talked about earlier, there are workers at the distribution centers that work the sorting equipment that takes packages in, looks at the labels, makes a decision of what vehicles do we have leaving that can get the package closer to its destination, eventually delivering that. Then, of course, there are people that operate the different vehicles, that drive the small trucks and the large trucks and fly the airplanes and so on, that actually move the packages through the system. Nobody goes from the origin to the destination, right? So the shipping system says, I'll deliver your deliver your package from the beginning to the end point that you're asking. But no one worker does that. It's a system that does it, not one device or one person. Now, if I think about all those things we have been talking about here for the last few minutes, I can segment out some of those functions differently, right? Some of those things had more to do with the endpoints, the people that put things in the box to protect the glass mug, for instance. And some had more to do with what the shipping company cared about, right? So if I separate out the work into functional layers, there's labeling, there's packing and boxing, what are the rules of what we can put into the shipping system. There's sorting, or maybe you call it routing, which is, hey, when I look at a label in the distribution center, how do I figure out which truck to put the thing on next? And then there's just moving the thing, right? Transporting from one place to the other. And you can even get into physical stuff like mechanics to fix trucks and, how do you keep things maintained so you have the ability to physically move the stuff. So let's talk about networking now. There's a thing called the TCP/IP model. It's also called the TCP/IP architecture, or even TCP/IP architectural model. And it's a way to think about modern networking that follows a related set of standards and protocols. And that model uses 5 layers, kind of like I broke down my shipping analogy into multiple layers of the way you think about the different components. And you see the names of those layers there. And yeah, for CCNA, you should commit that to memory over time. You probably will by accident, just by working through your CCNA studies. Now, the 2 upper layers are very much endpoint centric. That is, if you've got, say, your PC and it connects to a website, those upper 2 layers define things that the endpoints are primarily concerned with, and the devices that sit between them mostly ignore. Whereas the bottom 3 layers have more to do with what, say, the shipping company did, which is to move the packet, that's the right term instead of the package, from source to destination. And in fact, the network and data link layers are the ones that CCNA is primarily concerned with. So those are the network-centric layers of the model. Now, all the things in the model, the individual parts of them, sometimes they're standardized and sometimes they're not. That is, sometimes there's a standards body that has said, we've agreed to it, it's some government organization or some vendor consortium, but it's considered to be standardized. In other cases, it's just people got together and wrote it down and we use it. So we'll hear these things called standards and protocols. We don't really care so much for CCNA which ones met the formal standardization process or not. If it's used and it's commonly used, then we'll talk about it and understand it. All right, there was an original TCP/IP model, and it was defined in a TCP/IP document. All TCP/IP documents that define it are called RFCs. RFC stands for Request for Comment. Kind of a strange name, honestly, but it's a document, and you can look that up. You could go out and do an internet search on RFC 1122 and see the original model. You just note that it has a couple of different terms, and it's a 4-layer model. But over time, people began breaking out this link layer into 2 different models when they're talking about and thinking about what's going on, and name those data link and physical. And instead of internet, people started using the word network. So this model on the left, these words are the ones that you see most commonly used this day and age. All right, this day and age as in, last 3 decades kind of a thing. All right, now let's talk about what a TCP/IP network is. So a TCP/IP network is a network that's built using the protocols and standards defined in the TCP/IP model. All modern networks are TCP/IP networks, by the way. TCP/IP won, so to speak, against all comers when there was competition about which model would be used. And it's going to look familiar because it works a lot like that shipping analogy. You've got a source that's going to send. We've got a destination over here, server A, and these routers are going to be like the distribution center in the shipping system. So there's a packet. It's some bytes that need to get from PC1 to server A. That packet will flow to router R1, where a routing decision will be made about where to send the packet next. R1 sends the packet to router R2 next. R2 makes a decision and sends it over to server A next, and the packet is then delivered. So there's a move it to the next distribution center in shipping, move it to the next router in TCP/IP networking. Let's take a little closer look, though, at that packet. A packet first has an IP header. So a header is something that's defined in the standard or protocol document. In this case, the IP protocol document defines a header. And it says, hey, we're going to have an IP header, and then there'll be data behind it. The analogy, it's like your box you send in the shipping system. The IP header is like the label. It has the source address and the destination address that defines the sender, PC1, and the receiver, server A. And then the data is the stuff inside the box, by analogy, what we want to deliver over to server A. So that's a more detailed view of the packet that flows over to R1, and it's the same analogy here. R1 makes a forwarding decision, a routing decision to forward it to R2. R2 makes a similar decision to forward on to A. Now, a few other details while we're here. Those addresses are not postal addresses like they'd be in the shipping system, of course. They're a 32-bit address that for human convenience we write as 4 decimal numbers separated by dots. So we call those dotted decimal numbers, or at least the TCP/IP documents call them that. And these decimal numbers are each somewhere between 0 and 255 inclusive. All right, so that's the legal range in each octet is the word we use for each one of these 4 numbers. Now, if we were to look at the numbers in binary, each one of these 4 octets would represent 8 bits, the little b's are representing bits. So we get 8 bits plus 8 bits plus 8 bits plus 8 bits would give us a 32-bit binary number. Thankfully, you don't have to work with the 32-bit binary IP addresses very much. You can use dotted decimal numbers, which are much easier, which if you've never seen one before, you'd probably be a rare person, but that's what they look like. You've probably come across these even if you're just getting into networking from other contexts, right? By the way, if you took this dotted decimal number and converted each octet to its 8-bit binary equivalent, you get that binary version of the address down below. All right, back to network layer routing. Now we've got 2 destination servers on the right, each with a different IP address. Now we can have some insight into what routing looks like. PC1 sends a packet, and let's just say that packet has a destination address of server A's IP address. So there's R1's thinking, hey, it's destined to something that begins with 1011, kind of a group of addresses that all begin with 1011. Let me send those over toward router R2 next. It does. It gets to router R2, who sends the packet on to server A. All right, so those are some of the basics of how the network layer works in a TCP/IP network. The TCP/IP model, it defines 2 main protocols. It's got some others, but 2 main protocols. There's IP version 4. That was the original one that got deployed mostly in the 1970s and 80s, and we still continue to use today. And then its replacement, IP version 6, which you probably already use, whether you realize it or not. and it's becoming more and more used, and you can have them both installed and working on your computers all the time, and you'll learn some of both for your CCNA studies. Now let's talk about the data link layer. And we'll do that by using one example of a data link layer that's defined as Ethernet. Ethernet's defined by the IEEE. It's a standards body. It's defined in the 802.3 committee. And Ethernet actually defines both the data link and physical layer standards. And we'll focus on the data link layer here. There's another one called Wi-Fi from IEEE. That's the one for wireless communication. I'm sure you've heard of that one as well. And both of them, not just Ethernet, define both the physical layer details as well as the data link layer details. But just as an example, since this is our very first video, let's talk about the data link logic. Now we'll draw a generic Ethernet LAN, that is one with cables, between say a PC and a router with these lines that are perpendicular or parallel. That is, we're not concerned with the physical devices, just we want to know there's an Ethernet out there so we can focus on the data link layer logic. The data link layer is the set of protocols and rules that governs what you send across the link. It's kind of like traffic rules. You know, when the shipping company drives your box from your house to their distribution center, they have to follow traffic laws. Well, think of the data link layer like the traffic rules about what you can and can't do as you traverse this physical network. All right. So PC1, its logic, remember how we said it wants to send a packet and it sends a packet to the router and then the router sends the packet to the next router and so on? Well, to send the packet, it'd be like me throwing my box with a correct shipping label out of my front stoop and hoping it somehow gets picked up by the shipping company. Instead, the shipping company's actually got to physically come here and pick up the box and put it in their trunk. So what happens is, the equivalent, is that PC1 takes the packet and puts it inside another message, puts it inside a data link layer frame with a header and trailer that's defined by that data link protocol. In this case, ETH is short for Ethernet. So there's this idea of an Ethernet header and trailer. And that is what's street legal. That's what's allowed to be transmitted on the Ethernet physical links. And this travels over the Ethernet and is received by router R1. But R1's main purpose is to deliver packets. So it extracts or, quote, de-encapsulates the original packet. And now it can kick into that core logic of saying, hey, here's my packet, let me sort it, or in TCP/IP terms, let me route it, make a decision of where to forward the packet next. All right, so that's one of the roles of the data link layer, is to correctly encapsulate a network layer packet so it can be sent over the physical link. To accomplish that, the data link layer, certainly the LAN data link layers, define addresses. These are addresses that are local to each LAN. So for instance, when PC1 sends an Ethernet frame hoping to get that IP packet over to router R1, the destination Ethernet address in the Ethernet header refers to R1's Ethernet address over here on its left-hand interface. So the PC's interface has an Ethernet address, the left-hand router interface has an Ethernet address, and similarly, once this packet traverses the entire network and gets on the right side, it's going to be encapsulated in another different Ethernet frame. Why is it different? Because that Ethernet frame's destination address is server A's Ethernet address over on that side. So by analogy, remember how we had a truck on the left and then a plane in the middle and a truck on the right? Well, the local driver on the left, he might be in a town that's 1,000 miles away from the one on the right, okay? They don't know the roads in a town 1,000 miles away, but they know the local roads, right? So same way here. The Ethernet frame is just used on each link to deliver the packet to the next device, but not all the way end to end. So combining that thought together, here's our Ethernet frame. It delivers the packet to the router. The router discards that Ethernet header and trailer, makes a forwarding decision, re-encapsulates that in a new Ethernet frame, which delivers the packet to router R2, and then de-encapsulate and re-encapsulate in yet a third Ethernet frame. That all assumes here, I've got Ethernet, Ethernet, Ethernet. This link in the middle, the way it's drawn, it's an Ethernet WAN link, yes. Once you get further into CCNA, not too far, but a little bit further, you'll learn about wide area network links. And Ethernet can be used both as a WAN and a LAN technology. So stay tuned for more of that. Now let's talk about what to do with the book section, assuming you already own the books. As I mentioned, this video covers some topics found in Volume 1, Chapter 1, Section 1, called the TCP/IP model, and this video uses some different examples in the book, so you could glance over those and skim the network and data link layer examples in the chapter, but no big deal if you don't. However, that first section is pretty long, and it covers all 5 layers of the TCP/IP model, and I didn't get to those in this video. Maybe one day I'll have a video that covers the rest of that section, so make sure to read about the other layers if you have the book. Now, for all of you, let's do a review, and you should do this at some point. In fact, you could do it right now. And I have this idea called a terminology mind map. And the idea is you retrieve terms and definitions from your head and think about them and then reorganize them in your head. Now, if you've never heard of these, I've got a video about what to do with these, and then I've got a video to review the mind map I'd like for you to create related to this video. Mind map exercises like this are short, 5 or 6 minutes once you get the hang of it, so it's not a long exercise, but it's very useful for your brain. So it's good if you just turn around and do it now, watch the video that tells you how to do them, and then do one. However, it's better for you if you'll wait a bit, a day, 2 days, that kind of thing. And because of human nature, if you think, yeah, I'll wait, I'll remember to do it, if you schedule it, that's even best. So give yourself a calendar entry to say, hey, go do that mind map that Wendell mentioned in the video. All right, the mind maps start with a seed term, and there's the seed term for your exercise, TCP/IP, and you'll create a map of all the other terms you can remember from today's video as part of the exercise. So I told you I'd tell you what percentage of CCNA comes from the network and data link layer levels. Well, I did some math, and I came up with 75% combined. That's 45% from the network layer, and another 30% from the data link layer. So how did I come up with that? Well, there are 6 domains in the blueprint. Domain 6, none of those really can be categorized into a layer, so I just threw those out of the calculation. Then for some exam topics, the individual exam topics don't match a layer. I threw those out. And then I did a bit of math. The blueprint gives a percentage points from each domain. I categorized each individual exam topics as being layer 1, 2, 3, 4, 5. And then crunched it all out. So 25% come from the other 3 layers combined, and 75% from those 2 core layers, the network and data link layer. And does it really matter? Not so much. It's just kind of interesting to know. But as you learn, you'll keep categorizing mentally, hey, that's a network layer thing or a data link layer thing. And most of what you think about for CCNA will be from those 2 layers. Thanks so much for sticking around till the end of the video. If you like the channel, please subscribe and click the bell so you'll be notified when I come out with new videos. As always, leave me a comment, give me a like if you're interested and you like things. I'd love to hear a specific comment though. And hey, thanks for joining me. Look for you next time.